well as mathematical physicist also, right? And he also does research on statistical physics. So, but actually his presence with us, silakan. His presence with us here is well representing APCTP, mathematical physicist also, right? And he also does research on statistical physics. So, but actually his presence with us, silakan. His presence with us here is well representing APCTP, mathematical physicist also, right? And he also does research on statistical physics. So, but actually his presence with us, silakan. His presence with us here is well representing APCTP, mathematical physicist also, right? And he also does research on statistical physics. So, but actually his presence with us, silakan. His presence with us here is well representing APCTP, mathematical physicist also, right? And he also does research on statistical physics. So, but actually his presence with us, silakan. His presence with us here is well representing APCTP, mathematical physicist also, right? And he also does research on statistical physics. So, but actually his presence with us, silakan. His presence with us here is well representing APCTP, mathematical physicist also, right? And he also does research on statistical physics. So, but actually his presence with us, silakan. His presence with us here is well representing APCTP, mathematical physicist also, right? And he also does research on statistical physics. So, but actually his presence. Let me continue. To those who haven't been familiar with APCTP, it stands for Asia Pacific Center for Theoretical Physics. So it's actually part of ICTP, which stands for International Center for Theoretical Physics. While ICTP has the office, the main office in Trieste, Italy. APCTP has the main office in Pohang, Korea. So his visit, Professor Pierce's visit in our department is to share with us the information about APCTP as well as to establish agreement with UI, RIN, and ITB related to the activities that we are going to have, with APCTP. So his talk will consist of two parts. Maybe the time that is taken will be less to explain about APCTP itself, but important anyway. Then later it will be continued with the research talk. So I think without further ado, let's welcome Professor Paul Pierce. So time is yours.
Thank you very much, Aziz, for that very kind introduction. So today my presentation will be in two parts. I'll make some announcements and speak about our new network, about APCTP and ICTP, and then I'll call for questions. And then in the second part, we'll proceed to a more usual seminar. So to start with some announcements, we're very pleased that we have been funded for a 3-year network. And this network will be supported by ICTP in Italy, by APCTP in South Korea, and also by PCS-IBS in South Korea. The ICTP will be putting in 25,000 euros per year to support this network. And similarly, APCTP and PCS-IBS will be putting in similar amounts. The purpose of our network is to run various events, schools and workshops to stimulate engagement between various countries in this region. So in our network, there are 2 nodes in Korea, that's APCTP and PCS-IBS. And then we have nodes in Vietnam, Thailand, the Philippines. These were the original nodes. And in our second iteration now of this network, we're adding Indonesia and Cambodia. So we're very, very pleased that Indonesia is joining our network. And for most of you, the most important thing to realize is that you can learn all about the network by going to the PCS-IBS webpage. So if you just do a search in Google for PCS-IBS, and then you go to activities, you can pick Asian network, and it takes you to our ICTP Asian network web pages. And here you can see the structure that I just described of the various network nodes. I'm the coordinator, and Sergey Plak, who is the director of the Center for Theoretical Physics and Complex Systems at IBS, is the deputy director. Now, this year we'll be running 2 workshops in Korea, one at APCTP and one at PCS-IBS. In addition, we'll be running a school in November in Hanoi, and we want to bring as many students and faculty to that school as possible. So please stay informed and be aware. It'll take place early in November, so you should make plans accordingly. So each year we will have 2 schools and, we will have 2 or 3 workshops and a school. So next year in 2024, we will actually have a school and workshop in the Indonesian University of Indonesia campus. And that will take place sometime in the middle of the year, but the dates have not been fixed. But again, you should be aware that this event will take place. So this is about as much as I want to say today about the network, but please ask your colleagues, talk to Aziz and find out more about the events that are going on in our network. So you can see, for example, here are the 3 events planned for this year. The next announcement is that BRIN has decided to pay the membership fee so that Indonesia becomes a member country of APCTP. This is great news. It means that all academics and students across Indonesia, across all of theoretical physics, can benefit from programs offered by the APCTP. I should explain that the network is focused on key disciplines: condensed matter physics, complex systems, and statistical physics. But this connection with the APCTP, being a member country, this covers all of theoretical physics. And again, you can visit the APCTP web pages. Here they are. It's just apctp.org, and you can find out all about the APCTP and its many programs. So I should point out that both the APCTP and the ICTP offer a number of positions for postdocs. You should consider applying when you finish your PhD or after you've had some years of experience. It's a very good experience to have spend a year or more at APCTP or at ICTP. So you can similarly go to the pages of the ICTP. This is just ictp.it for Italy, and you can find out all about their programs too. So the third announcement is that BRIN is looking to establish a new category of young scientist in training position at APCTP. BRIN wants to create up to 20 positions exclusively for Indonesians. So this means you can apply, and it gives the possibility for you to go after completing your PhD to APCTP for 1 year. And this is a great opportunity for training and experience. So again, I encourage you to make the most of this opportunity. So I've only briefly covered these topics. You can find out more from your colleagues. Let me just pause and ask if there are questions at this point in time. So I must point out that today is my last day at University of Indonesia. On Sunday, I leave to go to Bandung Institute of Technology. I've already spent a couple of days at Rin, and all these institutes are involved in the network and fully on board and will support the network so that there is maximum benefit to students here. All right, so let's move to the second part of today's presentation. The topic for my seminar today is Yang-Baxter integrability in 2D classical and 1D quantum models. I'll be talking about a topic that probably most of you are not very accustomed to. I'll try to be describing some of the ideas from this area in simple words and pictures and diagrams. If you wish to learn more about this topic, I'll leave my copy of my slides with Aziz. And I've listed here a number of relevant references that you can go to read further. You know, when you start doing research and you pick up a typical paper, you read it, but you don't understand it. It takes a long time to learn new concepts. And usually what happens is you're exposed to some idea, you start to understand a little, and then the next time you start to understand a lot more, and so the process goes along. You shouldn't feel uncomfortable if you don't understand anything. Don't feel shy about asking questions. So anyway, anywhere through this seminar, please feel free to ask questions. So here you see this very distinguished gentleman, Rodney Baxter. He was my supervisor for 5 years in Australia, in Canberra, and he's Australian, and therefore he likes beer. And myself, I'm un-Australian because I don't much like beer, but that's another matter. Okay. So first, let me say a word about classical versus quantum. I'm going to be talking about lattice models. So think of the square lattice. I'm going to be working for the most part in 2 dimensions because 3 dimensions is just too difficult. But what is known by studying hypercubic lattices in D dimensions is that the relation between a classical and quantum model just drops the dimension by 1, so that a D+1 dimensional classical model can be related to a D-dimensional quantum model. So most of what I say will be regarding 2-dimensional classical models, but almost everything I say will apply in the quantum Hamiltonian limit where you're working with a 1-dimensional quantum Hamiltonian system. So when you start working with these lattice models, there are some very natural questions to ask. So when is a 2-dimensional lattice model exactly solvable or integrable on a bulk lattice? That just means a very, very large square lattice. So for the start of my talk, I'm going to be working in the framework of classical equilibrium statistical physics. So I assume you know what things like interactions mean and partition functions and so on. We will only get to a proper answer of this question towards the end of my presentation. If a lattice model is integrable in the bulk, is it also integrable in the presence of boundaries? So you can think of a strip, for example, in 2 dimensions. It has a boundary on the left and a boundary on the right, and this affects the statistical mechanics of that system. And saying it's integrable for an infinitely large lattice is not the same as saying it's integrable when you have boundaries. You can also ask, when is a one-dimensional quantum model exactly integrable? So the one-dimensional quantum model should be associated with the two-dimensional lattice model. And you might expect if the 2D lattice model is integrable, then so is the one-dimensional quantum model. Let me give some history. This subject has a long history. It started in 1925 with the Ising model. Ising was a student of Lenz, and what he did was solve a one-dimensional classical model of the Ising type representing a ferromagnet. So in an Ising ferromagnet, you have two valued spins, which are pointing either up or down. They take values plus or minus 1, and these spins interact through a temperature controlled manner, in a temperature controlled manner, and you get cooperative phenomenon if the interaction is attractive, that they tend to want to align in the same direction. And this provides an understanding in this simple toy model of ferromagnetism, how magnets work. People were interested in the two-dimensional model, but it wasn't until 1944 that Lars Onsager solved exactly the two-dimensional Ising model on the square lattice. And when I say solve, he calculated the free energy and the specific heat. During 1968 and 1971, after a long gap, Yang and Baxter introduced the Yang-Baxter equation, and they used that to study models which are referred to as the 6 and 8 vertex models, and these have connections with the quantum one-dimensional Heisenberg model. So this Yang-Baxter equation introduced a new technique for solving two-dimensional lattice models. In 1982, Baxter wrote his famous book, Exactly Solved Models in Statistical Mechanics, and in 1985, with Andrews and Forrester, they introduced an infinite family of models which are really multi-critical extensions of the Ising model. So at criticality, these lattice models have quite different behavior to being off criticality. If you're off criticality, correlations die away exponentially fast with some finite correlation length. At the critical point, the correlations decay only algebraically. So there are very different properties between critical and off-critical models. And in today's lecture, I'll focus on critical models. In 1984, the same year, Scherednik introduced the boundary Yang-Baxter equation, which opened up the possibility to solve exactly models in the presence of a boundary. In 88, Sklianin introduced double row boundary transfer matrices. So previously, these models were treated using a single row transfer matrix. I'll tell you more about the transfer matrices a bit later. And with a couple of my colleagues, I made a contribution in 2006 where we looked at Yang-Baxter integrable loop models. Again, this is a large family of models, but it includes models like polymers and percolation, which are of much interest to study in statistical physics. So let me tell you more about the classical two-dimensional Ising model. So here you see I have a square lattice. In the square lattice, there are two independent sublattices. You can see here one of the two sublattices is occupied with a state that I call 0. That means that those sites are frozen out. There's no statistics associated with those sites. On the blue sites, I put an Ising spin, so they can be up or down, plus or minus 1. And then these spins interact along the blue diagonal lines. So this is also a rotated square lattice, you see. So this is a description of the two-dimensional square lattice. If I look at, instead of along the blue lines, I look along the edges of the original square lattice, you see that if I have a 0, the neighboring sides can be plus or minus 1. So if I have a 0, the neighboring sides can be plus or minus 1. But if I have a plus here, then all 4 neighboring sides on that square lattice must be 0. So next to plus, you can only have 0. Similarly, next to minus, you can only have 0. So this is an adjacency diagram giving the allowed values of the spin as you move along the edges of the square lattice. And this A3 diagram is actually the Dinkin diagram of the simplest affine Lie algebra. It has a Z2 symmetry. You can flip it by interchanging pluses and minus. And this symmetry derives because we're considering the Ising model in a zero magnetic field. A magnetic field would favor either plus or minus, depending on the sign of the magnetic field. Now, the interactions along these diagonals are denoted by J. And then you have the Boltzmann factors. K is the Boltzmann constant, T is the temperature. And so associated with each of these elementary faces, if the diagonal goes this way, I have A and C, which take on values plus or minus 1. So there are a number of possibilities for interaction here. And this face weight has, it's a Boltzmann weight giving the, it's a Boltzmann weight depending on the interaction strength. So it depends not on just J1, but also the temperature through K1 and interaction in this direction. So all of these diagonals in this direction involve J1, and all the ones in this direction involve J2, hence there's a K2 here. So you see in this exponential, there is a product of A and C. They're the two plus or minus spins, so they interact. They're aware of which sign each other are, and they tend to point in this, tend to have the same value if J1, that is K1, is positive. R here is just a normalization factor. It plays no real role. Similarly, for this diagonal, we have K2, we have spins B and D now, but now there is a second constant, R bar, which again plays no role. So in statistical physics, to understand what's going on, you need to calculate the classical partition function. So what is the classical partition function? Firstly, we have a Hamiltonian or energy function A, which just tallies up the interactions in the system. So they're the sum over all of these pairs across this diagonal, so J1 by A by C, plus all the pairs in this direction, J2 by B and D. So this is just giving you the total energy of the system. The classical partition function is then a sum over all configurations. That's a sum over all spins. So for each of these blue sites, it can be plus or minus 1. So the number of configurations is just 2 to the number of those blue sites which carry a plus or minus spin. So we have a sum over spins, but this total Boltzmann weight, when you put it in here, you see there's a sum, you take an exponential, that becomes a product. So it becomes a product of all over all of these face weights. So it's a sum over spins, a product over all these elementary square faces along a row. And the Boltzmann weight now depends on the 4 spins, A, B, C, D, around that face, and they can be some that are 0. And those faces must satisfy, the configuration around those faces must satisfy this adjacency condition, otherwise this Boltzmann weight just vanishes, it's not allowed. I want to work with the Ising model at criticality. So these two interaction strengths are not independent if you want to be at the critical point. At a general point, the model is off critical. To be critical, you want sine of 2k1 by a hyperbolic sine of 2k2 is equal to 1. So that's a relation. So now instead of having 2 independent variables, we have 1. And that variable we're going to call u, the spectral parameter. It's spatial anisotropy, and it measures the relative strength between the 2 interactions. So this is just J1 on J2. We can now conveniently parameterize e to the 2k1 as cot u, e to the 2k2 as cot lambda minus u, and then these relations automatically follow. So everything is parameterized in terms of the spectral parameter u, and this variable lambda is called the crossing parameter in general, and for the Ising model, it takes the special value of pi on 4. Now, I explained to you that these normalization factors, the R and the R bar, are not really relevant to the statistics, that is to the physics. It's convenient for us to assign them these values in terms of u, and then basically we'll be able to remove those factors. So when you introduce these values for those normalization factors, Ru by e to the k1 becomes cos u, Ru by e to the minus k1 becomes sin u, R bar by e to the k2 becomes cosine lambda minus u, R bar u by e to the minus k2 becomes sine lambda minus u. So up to these normalization factors, which are trivial and will be removed, you see that the 4 Boltzmann weights that enter, that's e to the plus or minus k1, e to the plus or minus k2, are all expressed as very simple trigonometric functions in the spectral parameter and the crossing parameter. After you remove these trivial normalization factors, we can write all of these Boltzmann weights, the face weights, as one compact formula. So here I represent that Boltzmann weight diagrammatically as a square. This is one of the elementary squares of the original square lattice. The spins are A, B, C, D, arranged in this order. You see there is a little red arc in the bottom left-hand corner to say that's where you should start. That determines the orientation of this face. And provided that this is an allowed configuration, that is A, B, C, D, satisfies the adjacency conditions, the value of these Boltzmann weights are just sums of 2 trigonometric functions, sine lambda minus u and sine lambda, but lambda is just pi and 4, so sine lambda is just root 2. Kronecker delta AC, here sine u and sine lambda, Kronecker delta BD. So Kronecker delta AC just means A is equal to C. Kronecker delta BD just means B is equal to D across the diagonals. So there's 2 diagonal contributions to the interactions as we saw initially. In this second term, there's another term, square root of SASC over SB SD, where this capital SA is defined as sine A lambda on sine lambda, where you remember these spins, A, you can think of them as plus, 0, minus, but in this formula, we use the alternative labeling 1, 2, and 3. So A, B, C, D here in this formula is actually 1, 2, or 3. Now we have this adjacency matrix. So it's natural to ask about eigenvectors, in particular the parent Frobenius eigenvector, which corresponds to the eigenvector associated with the largest eigenvalue. And that vector has 3 components, S1, S2, S3. Remember, A can be 1, 2, or 3 now. That's the state of a particular site. And these SAs take the values 1, root 2, or 1. And when we act on that vector with the adjacency matrix, so you see 1 is allowed next to 2, which is to say plus is allowed next to 0. 0 or 2 is allowed next to 1 or 3, that's to say plus or minus, and 3 is allowed next to 2, which is minus is only allowed next to 0. So that's the adjacency matrix. You act on that state and you get the same eigenvector back again, but with an eigenvalue of root 2. We call that beta. It's actually equal to 2 cosine lambda, where lambda is pi over 4. And later I'll refer to this as a fugacity. We'll see more about that later. Now, the reason I introduce all of these face weights and this diagrammatic notation is that these face weights for the Ising model at criticality and 0 field satisfy the famous Yang-Baxter equation. So here we now have 2 distinguished gentlemen. This is Rodney Baxter on the right. This is C.N. Yang on the left, the Nobel Prize laureate. And this is a rather nice representation of the Yang-Baxter equation. You can see that this is really 3 faces of a cube, but then this is like 3 faces of the same cube, but relabeled. So you see we have A and B here, but A goes to the top and B comes to the bottom, and the C is pushed through from this side to that side. So now let me introduce the Yang-Baxter equation. The Yang-Baxter equation involves 3 bulk face weights. So the elementary squares represent Boltzmann weights, these W's. So when I draw a diagram like this, it means the product of these 3 Boltzmann weights. The dotted lines means that this spin state is identified with that one. This one is identified with that one, and so on over here. These are identified. These are identified. I could distort these square faces into rhombi, and then I could just move this point over to here, and I would have a rhombi here and a rhombi there, and it would say that this hexagon on the left is equivalent to a hexagon on the right. So the spin in the middle with a dark dot, that means it's summed out. So in that position, I should sum over the spin stage 0 plus or minus 1, and the same on this side. When I take the product of these weights and sum over the middle sides, the left and the right-hand sides are equal for all possible assignments of the spin states A, B, C, D, E, F around the perimeter. This is the meaning of the Yang-Baxter equation. And the nice way to think about it is you push this face on the left through to the right. You see it has spectral parameter U minus V. And then the spectral parameter of these two faces are interchanged. The U moves from the bottom to the top and the V moves from the top to the bottom. It has a nice diagrammatic interpretation. We will use this a lot in what follows. In addition to the Yang-Baxter equation, the face weights of the Ising model satisfy another relation that only involves two face weights. It's the product of two face weights. So there's a sum in the middle. This spin is identified with this one with this one. And so for all A, B, C, D, all values of the spins around the perimeter, the outside, this is actually equal to a scalar, rho u by rho minus u, where rho is just the function sine lambda minus u on sine lambda, and then a Kronecker delta. So it turns out to be independent of B and D, but A must be equal to C, otherwise it vanishes. So this is called the inversion relation. Up to this scalar factor, which you can absorb into the face weights on the left, it just says that the product of these two face weights is an identity, where the identity just ensures that as you move in this direction, here from left to right, all the spins stay the same. So B is B, D is D, and A will be the same as D, C, because of the Kronecker delta. Now that we've set up and understood the Yang-Baxter equation, now we can see why it's important. Let's look at transfer matrices on the torus and on the cylinder. To build up a torus, we take a slice through here, and we build up faces, but we identify the left and right edges. So we form a ring. And this is the transfer matrix. And now we have many spin states along the bottom and many across the top. The entries of this matrix, which depend on the spectral parameter U, are labeled by a row configuration on the bottom and a row configuration on the top. So for each assignment of a row on the bottom and a row on the top, that gives you one matrix element of the row transfer matrix T. Now what we want to do is to build up a large lattice. So we take this ring and we take the product of the transfer matrices many times, that is to the power capital M. So we put one of these rows on top of each other and keep going, and we identify the left and the right edge, so we have this topology. After applying the transfer matrix and summing over intermediate rows as we move along, we then take a trace. This identifies the top row with the bottom row, and so it closes the cylinder here to a torus. So this gives us the partition function on a completely periodic surface in 2 dimensions, that's the torus. To include boundaries, we need to move to a double row transfer matrix. We have 2 rows, one with spectral parameter U, one with spectral parameter lambda minus U. We sum over intermediate states in the intermediate row, but now we introduce new triangle boundary weights. On the right-hand side, we have a spectral parameter U, and on the left-hand side, lambda minus U. And these triangle boundary weights in principle can depend on the spectral parameter U in this way. So we're summing over all of the C's in the middle, and now the entries of the double row transfer matrix D are labeled by the row on the bottom, that's A's, and the row on the top, that's B. So this is a very large matrix. Now what we want to do is to build up a large lattice. So we apply the transfer matrix many times to build up a strip. And as we proceed, we sum over all of the intermediate rows. And now you see we build up triangles on the left and right. And again, I remind you, little dots means that the spin at this position is identified with that one, this one with that one, and so on. And this one with that one. Having built up a large strip, we then take the trace that identifies the top of the strip with the bottom, and that closes the strip to a cylinder. But now we have boundary conditions on the left and the right, denoted by alpha and beta. So now our classical partition function depends on alpha and beta. And I'll say more about what these boundary conditions are soon. Now comes the magic of the Yang-Baxter technology. The local Yang-Baxter equation and the local inversion relation implies commutation of the one parameter family of transfer matrices, whether that's T or D. So let's first look at the single row transfer matrix with periodic boundary conditions, and that's T. So Yang-Baxter plus inversion implies commutation of the one parameter family of transfer matrices, and that means it's Yang-Baxter integrable. And I'll say exactly why it's integrable and what you can solve for later. So consider you take the product of two transfer matrices, the first with spectral parameter U and the second one with V. If these commute, it means that this must be the same as T of V by T of U. So we basically want to interchange the spectral parameters U and V. So here is T of U along the bottom. We multiply by T of V, so we sum over the intermediate row of spins. And the left and right edges are identified. This is identified with this one, but we imagine that we cut it apart and we put in these two faces. These two spectral parameters just differ in sign. So the product of these two, that's described by the inversion relation. The product of these two is just the identity. So it says that this spin is equal to this one is equal to this one. This spin is equal to this one is equal to this one. And now we have periodic boundary conditions, so I can just move this one around to the left-hand side. And it, now if I look at these three faces here, that's one side of the Yang-Baxter equation. So I can push this one through, and it has the effect of interchanging U and V. But having pushed it through once, I can push it all the way through to the end, and it comes out here. This one is still sitting over there. That's a spectator so far. Now, because of periodic boundary conditions, this one can be pulled around to this side. And now these two, again, just differ in sign. So the product of these two up to a scalar is just the identity. So it can be removed again. I put in the scalar here and I took out the scalar there. And when I remove this, you see it's just T of V by T of U. So I have this commutation of these very large transfer matrices. Why is commutation important? If you have commuting normal transfer matrices, then they have a common set of U independent eigenvectors, and therefore they're simultaneously diagonalizable. So you can find the eigenvalues of these transfer matrices by finding eigenvectors which don't depend on U. That makes your life much, much simpler. So the eigenvalue spectra can invariably be found by solving functional equations. So these transfer matrices satisfy different functional equations, which you can then solve to get the eigenvalues. If these transfer matrices did not commute, the eigenvectors would depend on the spectral parameter, and it's almost impossible to make any progress on solving the problem. In the presence of a boundary, we need additional equations called the boundary Yang-Baxter equations. We have such equations for the right-hand side, shown here, and similar equations for the other side, just obtained by reflection. The boundary Yang-Baxter contains two bulk face weights and two triangle boundary weights. And on the left-hand side, you see they're combined in this way, and there's a dotted line here. So A there is the same as A here. And here we have B, C, D, E. This one can be G, and this one in the interior is F. F and G are summed over, as indicated here. We have the product of two bulk face weights and the product of two boundary face weights. So you see the boundary ones, we have a triangle in here. And we also have the spectral parameter, U or V. On the other side, what happens is you should think that this face comes in from the left, it hits the boundary. This face is a spectator, it stays as it is, but this face on the bottom bounces off the boundary and moves to the top. So it's just moved from here up to there. And in doing so, the U and the V from these two boundary triangle weights is interchanged. There is another local relation in the boundary case that's needed, and that's the boundary crossing relation. Again, there's a right and left relation. In this case, we have the product of a single bulk base weight with a triangle weight and up to a scalar factor that gives back a boundary triangle weight. So the Ising model satisfies all of these equations, which is quite remarkable. And to satisfy all of these equations for the Ising model, all you have to do is to set these boundary spins, A, G, E here, equal all 0, all +1, or all -1. And that means they're also set to that value on the right-hand side. So plus means all the spins are up, minus means all the spins are down, and 0 corresponds to a free boundary condition because the next spins in, these are frozen if they're all 0, but the next spins in can be either plus or minus, and that's a free boundary condition. So there are 3 integrable boundary conditions for the Ising model. What about commutation? Now we want to show that du dv is equal to dv du. So here is d of u. All the intermediate rows are summed out. Here is d of v in the upper position, double row. And now we want to move things around graphically. So we cut it open in the middle. Using the inversion relation, we put in these 2 faces. Their spectral parameters differ by a sign. And now we move this one to the right. Each time we move it to the right, it interchanges as a v and a lambda minus u. So v comes to this position, lambda minus u to that position, and this one's pushed all the way into the corner. Likewise, on this side, we push it all the way to the corner, and again, these 2 rows are interchanged. Now we cut it open again. We put in these 2 faces. We always put in faces with a spectral parameter given by the difference of these 2. That means through the local Yang-Baxter equation, we can push this one to the left, and we can push this one to the right, and it interchanges the u's and v's. So we come down to this position. But now all we have to do is to replay everything in reverse in slow motion, and we will get back to the original picture, but with the u's and v's interchanged. So now we can push this one back into the center, and this one back into the center, and it will interchange the u and the v at the bottom. No. Okay, so what we've done is accumulate on the left-hand side, one side of the boundary Yang-Baxter equation. Here's the right one. So from the boundary Yang-Baxter equation, we can bounce this one from here up to the top. So on this side, we bounce this one from here up to the top. So when we do that, these are the pictures that we've got. So we just bounce these faces up to the top. Now we can pull this one in, and we can pull this one in until they meet. And when they meet, because of the local inversion relation, they annihilate. Because each time you use the local inversion relation, there are some scalar factors which we accumulate, but they're all removed at the end. So they are annihilated, and we're left with this position. And now we can pull these in and this in, they meet and they annihilate. And we're finally left with this. And after this process of pushing all of these faces around and interchanging the spectral parameters in adjacent rows, we end up where we have a double row transfer matrix with spectral parameter V at the bottom and spectral parameter U for the double row transfer matrix at the top. I said classical two-dimensional systems are related to one-dimensional quantum systems. How does this come about? Well, we have commuting families of transfer matrices, either T or D. They yield an infinite number of mutually commuting conserved integrals of motion, which we denote by HK. And they're obtained just by doing a simple Taylor series for small u. So for the different powers of u, you pick up a term in the Taylor series expansion of this transfer matrix. And it's clear because this is a one parameter family of commuting matrices that these HKs, all of these Hamiltonians, mutually commute. H0 for the periodic case is just a cyclic shift operator, and H0 on the strip, that is for the double row transfer matrix, is just the identity operator, I. If you look at the first Hamiltonian, H1, this is the one of most importance usually, and look at the Ising model with periodic boundary conditions, then that first Hamiltonian gives you a quantum Hamiltonian, which is this one. So the transfer matrix is actually an operator, and write these Hamiltonians in terms of Pauli spin matrices. And when you do so, it takes this form, and so it's related to the Ising model in a transverse field. That's a quantum system, one-dimensional. It was first solved by Fute in 1970. You can do the same things for the double row transfer matrix and look at H1, except now, in addition to these bulk terms, because you go from j equals 1 as a neighbor, again, around the cycle, next one is n. So n plus 1 is the same as 1. But on the strip, you don't go from n back to n plus 1, which is 1. Instead, you have an additional boundary term. So there are boundary terms of j equal to 1 and j equal to n. But still is an integral quantum Hamiltonian. Now, algebraically, it's interesting to ask, when do we get a solution to the Yang-Baxter equation? Why does the Ising model give a solution to the Yang-Baxter equation? So here again are the local relations, but now I write them in terms of elementary phase transfer operators xj. So in this position, you have some j. As you move to the right, j increases by 1. As you move to the left, j decreases by 1. These two have the same j, so they're at the same position. When you multiply, you sum over the intermediate spin, and this is just the product of these two trigonometric functions, where now I introduce SU for sine u on sine lambda. Similarly, for the Yang-Baxter equation, there's 3 faces on the left, 3 faces on the right. I draw it somewhat differently now. These spins are identified, A and D and D. The orientation of the faces are given by the little red arcs. And now you can see this is a product of xj of u, that's this one. And then we increment j by 1 because we move to the right. So xj plus 1 of u plus v by xj of, we're back to position j of v. And on the right-hand side, we have xj plus 1 of v by xj of u plus v by xj plus 1 of u. So this is an operator form of the local Yang-Baxter equation and inversion relation. Now you can decompose these space operators into the sum of 2 terms. We notice that in one case we had a Kronecker delta involving AC. That means it was diagonal in that direction. And the other term was when it was diagonal across the other diagonal. So we basically have, if it's acting in this direction, we have a Kronecker B prime, and we have a Kronecker AC in the second term. The trigonometric weight for the first term is S of lambda minus u, and in the second term, S of u. We can denote the contributions coming graphically from the face this way. So here, everything is diagonal in this direction. So B is equal to B prime. A and C can be different. So these arcs are actually denoting domain wall boundaries. And here A and C must be the same, and here we have domain wall boundaries going this way. So here everything is the same moving in this direction. Here everything is the same when you move from left to right. These domain wall boundaries are actually appearing in the study of knot theory. These are actually segments of strings, and they have isotopy properties and so on. And the Templey-Lieb algebra also arises in the study of knots. So this decomposition here, this one is just the identity. Everything acting in this direction remains the same. But this term is not the identity. B is not equal to BC. A is equal to C. So this is a new term, and we denote that operator by EJ. It's at position J. As you move to the right, J increments. Now these operators, EJ, satisfy some special relations which are called the Templey-Lieb algebra. EJ squared is equal to beta EJ. Beta is just 2 chi lambda. For the Ising model, that's just root 2. But in addition, EJ by EJ plus or minus 1 by EJ is EJ back again. These relations in this algebra first arose in the work of Templey-Lieb when they were studying percolation. And indeed, you can study the percolation model using this algebra. The proof is easy. Each phase decomposes into 2 terms, either the identity or this Templey-Lieb operator, either this phase or that phase. And then you just substitute them into these phases. You get 2 by 2, 4 terms here. and 2 by 2 by 2, 8 terms here, and 8 terms here. And then you use these relations, expand out, and you find that the left and right-hand sides of these relations are identical. There is a very nice diagrammatic interpretation of the Template-Lieb algebra coming from the interpretation in knots, where these are called monoid algebras, monoid diagrams. Either move in this direction or that direction. And when you start multiplying them together, remember this side is identified with this one, this one, this one, you can form some closed loops. And when you form a closed loop, that generates a scalar contribution beta, which is 2 cosine lambda, the loop fugacity. So in this diagram, when you multiply EJ by EJ, it should be beta by EJ. So you can see what it means is you just remove this central part of the diagram containing the loop, and you replace it with beta on the outside. You do everything diagrammatically in terms of strings. If you multiply EJ by EJ plus 1 by EJ, it should be equal to EJ. That's this diagram. There's nothing happening on position J plus 1, so that's just a straight strand. So you just identify everything by following the strands. So this strand goes from the top to the bottom. You can pull it tight. And again, you can remove this middle portion. There are no closed loops, so you don't pick up any closed factors. You just remove this portion and replace it with this straight line. You collapse this part down and you're left with this half loop and that half loop, which is the diagrammatic representation of the generator EJ. So diagrammatically, a face is decomposed into a product, a linear combination of these two monoid diagrams with different trigonometric prefactors. Now, so that means to find a solution of the Yang-Baxter equation, you only have to find a representation of this algebra. There are 3 known types of representations for the Template-Lieb algebra. The first is height or restricted solid on solid models. These include the Ising model and generalized Ising models, where you have a finite number of spin states. You can have spin or vertex models, or you can have loop models, which include polymers and percolation. So I'm focusing here on the Ising model as an example of RSOS type, and I'll say something about polymers later as an example of the loop representation. In terms of these operators EJ, they're Hamiltonians. For a periodic system takes a very simple form. It's just the sum of the EJs up to a sign. Let me skip that because it's a little technical. Let me now talk about functional equations. So we have commuting transfer matrices, but why should that imply that the model is solvable? How do you go about solving them? So in all cases that we know of, if you have commuting transfer matrices, these transfer matrices satisfy certain functional equations. The simplest example is what's called inversion identities. An inversion identity takes the form where you multiply T of U by T of U plus lambda. You get a scalar multiple of the identity with some function to the power of the system size. That's the number of faces in a row, n, plus a second scalar function, F2, raised to the system size, n, the number of faces in a row. But this time, this one involves the spin reversal operator. This is the operator that just acts to reverse the spin at each side. Up goes to down and down goes to up. That spin operator is a symmetry of the model, so it commutes with the transfer matrices. In the case of a double row transfer matrix, the same functional equations hold, but now there are additional order 1 factors. So you pick up an order 1 scalar factor here and an order 1 scalar factor there in front of these nth powers. Remarkably, these inversion identities are satisfied for a number of different models. Firstly, there's the Ising model. We're going to consider the critical behavior, so we're going to consider the description of these models in the continuum scaling limit. So we shrink the lattice spacing to 0. We go to a continuum. These models are then described by a continuous theory, and in criticality, that continuous theory is a conformal field theory. This number C, called the central charge, is the main number that characterizes that conformal field theory. There's the free fermion 6 vertex model, which has C equals 1. There is critical dense polymers, which has C equals -2. I'll say a little more about this later. And then there is dimers, which also has C equals -2. For the Ising model, this function F1 is just cosine of 2u, and F2 is just sine of 2u. Now, the spin reversal operator, J squared equals the identity, so the eigenvalues are just J equal to plus or minus 1. And denoting the eigenvalues of this bold T by non-bold T of u and T of u plus lambda, lambda is pi and 4 for the Ising model. The eigenvalues must satisfy this functional equation. T of u by T of u plus pi and 4 equals cosine 2 of u to the nth power plus J sine of 2u to the nth power, where J is plus or minus 1. Now, it turns out this is relatively simple to solve these functional equations. The right-hand side here is just a polynomial, a Laurent polynomial with period pi on 2 of degree 2n in the variable z equal to e to the iu. So this polynomial is characterized by its zeros. These zeros occur in the complex plane, and they occur in pairs on the line real u equals 0 and real u equals pi on 4, and the two members of that pair have the same common value of their imaginary part. So at some specific height, there are two vertical lines. You must have 1 0 here and 1 0 there, and their positions differ by pi on 4. So if I assign 1 to this one, then this one has the 0, which is just shifted by pi on 4. But if I assign the second one to this one, then because of periodicity, when I shift a pi on 4 back again, this one just has the 0 that was originally here. Each pair of zeros can arbitrarily be shared out, therefore, between these two eigenvalues. And I can do that for each pair, and there are n pairs, so that's 2 to the n different solutions I can obtain for these eigenvalues. And there are exactly 2 to the n eigenvalues for these transfer matrices. So this simple argument gives me all of the eigenvalues of that transfer matrix. Excuse me. All right, next I want to talk about the finite size behavior, critical behavior, universality, and relations to conformal field theory. So at criticality, the continuum scaling limit of a 2D lattice model is described by a conformal field theory. That's characterized by a single number called C, the central charge. We've got these inversion identities, we can solve them, but what can we solve them for? What are the relevant physical quantities that we can obtain? Firstly, you can obtain the bulk free energies. That's a non-universal property. You can calculate the boundary free energies. Again, that's non-universal. But you can also use finite size behavior to calculate conformal data, such as this central charge, but also conformal weights. These are additional numbers related to critical exponents of the statistical physics models, which characterize the universal behavior and the conformal field theory. You can also calculate generating functions for the conformal spectra. That's described by conformal characters on the strip and conformal partition functions on the torus. So what happens when you move to a larger and larger system in taking the system size off to infinity and the continuum scaling limit? If you take the log of the eigenvalues of the single row transfer matrix, this is an extensive quantity. So you pick up a term that grows extensively with the system size n, and the coefficient gives you the bulk free energy. There is no boundary term when you're on a torus. So there's no order 1 term. The next term down in this larger n expansion is of the order 1 on n. And these terms relate to the conformal field theory in the continuum scaling limit. So you see the central charge appears here. The delta, it depends which eigenvalue you're looking at as to which delta you obtain. And theta is just pi u on lambda, pi by the spectral parameter on the crossing parameter. K and k prime are integers, which label all of the different excitations in the spectrum. And then there are further terms which we're not interested in. The difference on a strip is you take half of the log of the eigenvalue. You now get n times the bulk free energy again, that's the extensive term. Now we have an order 1 boundary term coming from the boundaries on the left and the right. And then there's a conformal correction again, but this conformal correction is somewhat simpler. to calculate the bulk free energies, you have to use Fourier transforms to solve the functional equation. To calculate the finite size corrections, these eigenvalues are given by contributions from these various zeros, so they're given by a sum. In the continuum scaling limit, that sum becomes an integral. So the difference, it gives the corrections as in this asymptotic behavior. And so the difference between the integral and the sum, that's described by the Euler-Maclaurin formulas. So when you use these, you can calculate the conformal properties C and the conformal weights delta. For the critical easing model, you obtain C equals 1/2, and delta can have 3 possible values. Boundary case, you obtain these 3 values when you take plus 3 and minus boundary conditions on the right, and just plus boundary conditions on the left. This critical behavior is related to the operator content of the conformal field theory. So the 2-dimensional easing model was solved exactly by Onsager for the free energy. For the magnetization, it was solved in 1952 by Yang, and the exact critical temperature of the isotropic model is given by this equation. From the free energy, you can look at this behavior as you approach criticality. So these quantities were obtained off criticality. At the critical point, psi behaves as T, the temperature minus the critical temperature, given by this equation, to the power 2 minus alpha. So alpha is the specific heat exponent and takes the value 0 here, and that's indeed what you get. And that critical exponent alpha is simply related to a delta that appears in the spectrum, delta epsilon, which is the energy operator. Delta epsilon is equal to 1/2, and that's what you obtain from the scaling relation familiar in statistical physics. So delta epsilon appears here and here. It's repeated twice. There's a symmetry, a Z2 symmetry in this catch table related to the spin reversal symmetry that is interchanging 1 and 3. So because of that symmetry, there are 3 operators in the easing model: the identity, the magnetization, and the energy. The magnetization vanishes at the critical point, and it goes to 0 as T goes to Tc with an exponent beta, which is 1/8. The delta related to the magnetization, delta sigma, is related by scaling relations to this critical exponent beta just by 1/2, and that takes the value 1/16, which occurs in the middle row here. So it's repeated twice. So the operator content is described by the identity operator, the magnetization, and the energy operators, and they are conjugate to the plus boundary conditions, the free boundary conditions, and the minus boundary conditions. And they have the 3 values in the first column of this little table called the catch table. So all other critical exponents, there are many different critical exponents, alpha, beta, you can define other critical exponents, gamma, that's a susceptibility, and so on, delta. All of these critical exponents are related to just 2 non-zero conformal weights, namely delta sigma equals 1/16 and delta epsilon equals 1/2. You can obtain all of these critical exponents by using known scaling relations. I want to finish briefly by discussing critical dense polymers. This is actually related to one of these logarithmic minimal models, which depend on 2 integers, p and p prime, which are co-prime. Now lambda is p prime minus p by pi over p prime. So the easing model would relate to p equal to 3 and p prime equal to 4, and then this value would just be pi on 4. The face operator is the sum of these 2 faces, which are related to the identity and the Templey-Lieb generator. So now we think of these operators purely diagrammatically, and we think of these as these segments, string segments, as loop segments. They are segments of a very long polymer. So in the case when p equals 1, p prime equals 2, we have a loop gas solution because it's built from the known Templey-Lieb representation. And if you have these boundary conditions, the polymer must enter here. it must wind around. There are only these two faces, so it must pass twice through every face, and eventually it must come out here. So the partition function is just a sum over all possible loop configurations. Each face can be in that or that configuration, and they have their Boltzmann weights. And this is an integrable model now. And you can see as you go to the continuum scaling limit, this loop segment will actually fill space. It's a piano curve, which means it has fractal dimension equal to 2, and that's related to a conformal weight in this theory. And the loop fugacity, you're not allowed to have any closed loops because beta equals 2 cos lambda. If lambda is pi on 2, that vanishes, and that means there are no closed loops. So you get space-filling dense polymers. In this model, there are no local degrees of freedom. There's no plus, minus, or anything like that. There's only non-local degrees of freedom in the form of extended polymer segments. And these transfer matrices act diagrammatically on linked states, but nevertheless, you can work with them. So I just want to point out some of the differences between these two types of theories. The Ising model is a very simple rational CFT, and it corresponds to free fermions. So it has central charge of half, crossing parameter pi on 4. Critical dense polymers, on the other hand, is not a simple rational theory. It's actually a logarithmic theory. It relates to symplectic fermions. Its central charge is -2, and its crossing parameter is pi on 2. Here we saw we only have 3 independent conformal weights. Over here in the logarithmic setting, life is much more complicated. There is an infinitely extended catch table of conformal weights, which means this system exhibits an infinite number of different critical exponents. All of these critical exponents are given by a simple formula, the Katz formula, in terms of P and P prime, and R and S. So R and S just give the positions, R and S, the row and column labels in these tables. And here I've just summarized the conformal weights and critical exponents for the Ising model, and over here for this logarithmic theory. So you just should be aware that systems like polymers and percolation have very, very different behavior to simple rational models like the Ising model, POS models, and these RSOS models. So that brings me to my conclusion. Finally, we get to some answers into a summary. So a two-dimensional lattice model is Yang-Baxter integrable in the bulk whenever the local Yang-Baxter equation and inversion relations are satisfied. If a bulk lattice model is integrable, then the lattice model is also integrable in the presence of integrable boundaries, that is, those that satisfy the boundary Yang-Baxter equation. For a given bulk theory, you can have many solutions to the boundary Yang-Baxter equation, allowing for many different integrable boundary conditions. In the Ising model, we had plus, minus, and free boundary conditions. Actually, these integrable boundary conditions can be constructed systematically, starting with a simple vacuum boundary condition and applying a fusion at the boundary. So if you have a spin half, you can fuse it with a spin half and get spin 1. You can do this on the boundary, and what it does is generate new boundary conditions for you. And in the rational theories, this process closes, whereas in the logarithmic theories, that process does not close. You get an infinite number of such boundary conditions that are integrable. A 1D quantum model is integrable whenever its associated two-dimensional lattice model is integrable. You can calculate the bulk and boundary free energies of these integrable systems. You can also calculate the conformal data, and that's solved by that's obtained by solving functional equations. Bulk and boundary free energies are non-universal. Conformal data is related to the critical exponents and critical behavior of the model described in statistical physics by critical exponents. So you obtain universal behavior. Some simple models satisfy inversion identities. I indicated 4 such models. More generally, integrable models satisfy much more complicated systems of functional equations in the form of T and Y systems, which go well beyond this. For rational theories, such as the Ising model, the number of scaling fields in the theory is finite. For logarithmic theories, such as polymers and percolation, there are an infinite number of scaling fields. And finally, for rational and logarithmic theories, the conformal weights of the scaling fields are organized into finite or infinitely extended catch tables. So with that, I thank you for your attention, and I welcome your questions.
Yeah, if any question? Good.
Hello there. My name is Prakoso, MJ Prakoso. I'm kind of a beginner here about Yang-Baxter equation, but how did that equation has been brought up in the first place? I mean, is it basically an expansion of Boltzmann distribution, or Boltzmann partition? And secondly, in what extent do we need to use the Yang-Baxter equation?
Good, thank you for your question. Let me point out that when it comes to condensed matter physics, I'm a beginner, but one of my roles as the coordinator of our network is to attend our annual schools and listen to endless lectures on condensed matter physics. And at the start, I knew nothing, but now gradually, after 3 years of attending such schools, I'm beginning to understand and appreciate the work of my colleagues. And as I say, you should expect learning a new subject to be overwhelmed at first. So thank you for your question. Actually, if you go back to the solution of Onsager, it was a tour de force using Lie algebras, which is very surprising because Onsager was a chemist and he got his Nobel Prize for working chemistry. But nevertheless, his work is quite remarkable. And after that work appeared, many people tried to understand what was at the center of his calculation that made it work. And it took many, many years before people realized that the important property was that these transfer matrices were commuting. And then they wanted to understand, why are these commuting? What relation is it that leads to the commutation? And ultimately, people like Jim McGuire, Cian Yang, and Rodney Baxter understood that this originates solely from local relations. And then the whole power of Yang-Baxter technology became available.
Well, judging by the diagram show, I mean, there are many loop fugacity and anything of the sort. Well, do you think that it is possible to be applied for topological phases of matter?
There are topological phases of matter. People study strings, and this occurs in knot theory, for example. And these strings have isotopy properties. So this description, let me emphasize, only happens at criticality. Only at criticality can you represent what's going on in terms of a loop gas and isotopy of strings. As soon as you move off criticality, you move away from planar geometry to a hyperbolic space, and these properties of isotopy break down. But in topological quantum field theory, you're familiar that such properties of isotopy appear all the time. When you study defects in condensed matter physics, they have properties of isotopy.
Yeah. Any more questions? Pak Rahim? Ada pertanyaan nggak? Before the others may think about what question they may ask, I was wondering about your first part of your first sentence about the relation between quantum model and classical model, where is it that the d-dimensional classical model is mapped to, or?
So I can express this argument very simply. So two-dimensional models are built up one row at a time. You apply a transfer matrix. You can think of writing that transfer matrix in terms of operators, as I did for the transverse easing model, where Pauli matrices came in. So you can write the transfer matrix is one-dimensional. You can write it in terms of operators. So you have a one-dimensional theory of operators.
Okay.
Associated with a two-dimensional lattice model. That one-dimensional theory is precisely the quantum model. If you take the 6 and 8 vertex model, studied by Yang and Baxter and Elliott Lieb, the 8-vertex model in general is off-critical. The 6-vertex model is the critical manifold. And if you take the quantum Hamiltonian limit there, you obtain the anisotropic Heisenberg model in the most general sense.
Okay, okay. So it doesn't have to do with in the quantum model you actually have operator rather
I have
than
operators.
just.
So
Oh,
remember
you do. Okay.
that I have operators. I call these space operators xj. And these operators xj just relate to an identity and to ej. This ej is an operator. So it's like a Pauli matrix. So for some systems, Pauli matrices is convenient. That's when you're
Okay.
using spins.
Mm.
And this is what condensed matter physicists and so on are used to thinking of. But when you describe systems like polymers and percolation, it's natural to work in terms of different operators that build up your Hamiltonian, that are the basic objects, and that object is EJ. That's a Temperley-Lieb generator. And there are many generalizations of the Temperley-Lieb algebra, which occur for different models in the loop setting. And you can see that the Hamiltonian is very simply written in terms of the EJs. This is possible also in this J in here. This sum of Pauli matrices is just a single EJ. That's the relation.
Okay. Okay, thank you for that clarification. Any other questions from other audience? If not, let me add one more.
Can I have questions?
Oh, from the
Online.
Zoom. Yeah, I'm forgetting that we also have Zoom. Yeah, silahkan nanya di itu.
Yeah, okay. So in the earlier slides, you introduced this new representation local block with parameters U and V. So I don't see, is it necessary for U and V to be different phase or can be the same, so they are degenerate?
I'm sorry, can you repeat? I use variable U and what was the second one?
Yeah, you parameterize this into different blocks and U and V in the neighbors blocks.
What V?
U and V. So they are different blocks in the previous slides.
What T for tango?
Yeah, in the Young-Baxter, the next slide, in the Young-Baxter.
Yes. So
Yeah, you have this U and V.
one value for the spectral parameter. V represents another value for a second spectral parameter. For all assignments of these two spectral parameters, this equation must hold.
Are they need to be different or they
So,
can be same?
sorry to cut you up. It's like saying you have a function f of x and you have a function f of y. It's the same function, you're just replacing the dummy argument. I have two dummy arguments here, u and v. When you have commutation, it's trivial that two transfer matrices commute when both spectral parameters are the same. If v is equal to u, then clearly the left-hand side and the right-hand sides are the same. So you must allow for this parameter to be different from that one. And then you find that for all different parameters, u and v, they actually commute. Does this answer your question?
Yeah. And also, there's a criticality when it reaches lambda. Is this related to phase transition or just, is this not always, yeah.
So now you're talking about lambda. Lambda is a property of the model. So for the lambda is pi on 4. For polymers, lambda is pi on 2. In general, for these more general models I discussed at the end, lambda is p prime minus p pi on p prime. So that says it's just a rational fraction of pi. In all of these models, it turns out that lambda is just a rational fraction of pi.
Yeah, well, my question is just about when you have U and you say earlier that U is less than lambda, and is this lambda is related to physical picture when they have phase transition, or just a parameter, the maximum parameter that U cannot be reached?
Now I understand your question. So let's look here. Here are the Boltzmann weights. A Boltzmann weight is a probability. A probability should be positive to be physical. You don't throw a dice and get one value with a negative probability. So Boltzmann weights W must be positive. Here we have sine lambda minus U. This constraint is to ensure that sine lambda minus U is positive. In this range, remember lambda is pi on 4, sine of U is also positive. These essays are all positive, so you can extract the square root. Every term here is positive. The Boltzmann weights are positive. If you go outside of this range, you can end up with negative Boltzmann weights, and that can lead to unphysical behavior. I should say that there are many models that have negative Boltzmann weights, and yet they still make sense. And the difference is this is a unitary theory, and other theories are non-unitary theory. But in this circumstance, and for the purposes of this introductory lecture, I only discussed parameter ranges where the Boltzmann weights are all positive or zero.
Okay, thank you.
By the way, is that you, Ghaffar?
Yeah, it's me, Alice.
Yeah, I didn't recognize your voice though. Since you are not turning on your video, I cannot see your face. So Ghaffar is actually one of our students.
Yeah, I
Yeah,
know he was at his YST at APCTP.
Oh, okay. Yeah. Yeah, I remember. He was one among the delegates from Indonesia. I remember, yeah. Okay, thanks, Ghaffar. For any more question from here, from the audience over here? Otherwise, I have one more. I saw from your description of the problem of the square lattice icing model. To my understanding, the way you set up the model, you put spins alternatingly, right?
Yes.
With the blue dots, whereas the one, the circle without.
Yeah, one sublattice is frozen out.
So
Now,
basically, it does that mean that you only have the side, but you don't have spin?
it means that site is frozen out, and the state at that site does not contribute to the statistics.
Yeah, but what
and
does that
therefore not
basically
to
mean?
the physics. So you might think I should not.
I mean,
put
is
in
it
these
equivalent
intermediate-
to not having any? Okay, we may have the atom, but we may not have the spin in there.
Yeah, so let me explain what's going on here. You might think, okay, I shouldn't worry about these states. I should only focus on the blue ones. And then I should build up a transfer matrix which goes diagonal to diagonal.
Okay.
And then I don't need those frozen sites.
Okay.
If you do that, those transfer matrices do not commute.
Okay.
There are many subtleties in working with Yang-Baxter equations. When you set it up this way and transfer row to row, now they commute.
Yeah.
And part of the reason is that they're associated with this Dinkin
So
diagram.
they do play a role in the interactions.
They play a big role in the interaction, the encoding of the
Okay.
interaction in terms of this adjacency matrix or diagram, which is a Dinkin diagram of an affine Lie algebra. So what happens is I can add more and more values for the spins here. So I could have AL, and it would go 1, 2, 3, 4, up to L. L is finite. This gives you the RSOS models.
Mm.
And it's associated with the affine A-type Lie algebras.
Mm.
You can look at affine D-type algebras, and they have a Dinkin diagram that is a straight segment, which then has a fork, a double fork on the end. That's the Dinkin diagram for a D classical Lie algebra. And you can think of those nodes of that graph as states of your lattice model, and they're all solvable. So if you have a simple D-type graph on 4 nodes, the middle one is frozen out, and you have 1, 2, 3, and there's a Z3 symmetry. This is actually a 3-state Potts model.
I see.
And then you can go to the exceptional classical Lie algebras of type E6, E7, and E8, and each one of those is associated with an exactly solvable classical two-dimensional lattice model. And this is quite typical. Integrability is underpinned algebraically by Lie algebras. So if you want to think algebraically, here I spoke about temporally Lie algebras, but if you want to think algebraically, it's the Lie algebras that underpin much of the integrable structure. There's a topic better suited to mathematicians.
Yeah. But I just remember one thing that I want to add my question. What about the K1 and K2? It looks to me geometrically, to our, usual physicists think of from the intuition. Probably most of us will think that there shouldn't be any difference.
No,
Yet
if you want it to be isotropic, J1 is equal to J2. K1 is equal to K2.
Okay, so you make
So
it general. So that,
with the square lattice, there are two different directions, differing by 90 degrees. You can consider them to be the same to get something isotropic. For the critical model in the conformal limit, you only consider the isotropic case. But the spectral parameter U, which plays such a crucial role in the Yang-Baxter description, that's a measure of spatial anisotropy. So in the isotropic case, there is no U. To vary U, you must vary the spatial anisotropy. And this gives you the one parameter family of commuting models. This spatial anisotropy in the renormalization group language is a marginal operator. You know, there are relevant and irrelevant operators in description of critical behavior. This one is marginal, and it enters this way in the Yang-Baxter description. So you must start by considering anisotropic models, and then you can move later after you've solved the model to the isotropic situation.
could you give us some physical example of what actually would distinguish between the left or right diagonal interactions, like in terms of perhaps the existence of something in between the two spins, or what?
You could imagine a physical system where the the geometry is not determined by squares; it may be determined by rectangles, and the interactions in this direction can be different to the interactions in that direction. Because when they're closer, the interaction is stronger. When they're further apart, the interaction is weaker.
Yeah. Okay, thank you very much. I should give back the opportunity for asking questions to the audience over here. Any more? Our time is actually limited to 3 o'clock. It's already 3. Yeah. So I guess with this, we finished the question and answer sessions. And let's again give applause to our speaker. Ini pakai itu ya? Okay. As our custom, we usually give our speaker just a certificate, just for a memory for you to bring home. Siapa yang ngasih nih? Pak Budi deh. Pak Budi, di sini yang senior. Ada di sini konsekuensinya. Ada materi ya? Ya nggak apa-apa Pak Budi lah. Nggak ada materi. Ya, di foto ya.
I should point out that when you attend our network schools, at the end we give you a certificate of attendance.
Yeah, this is Dr. Budi Kurniawan, one of our faculty member. Setelah ini kita foto ya. Agak ini kali berdiri apa? Ya nggak apa-apa lah, udah nggak apa-apa. Udah cukup.
Thank you very much.
So on behalf of Physics Department, all the audience in this room, we thank you very much, Professor Paul Pierce, for your nice and informative talk. Although probably from the whole presentation that you gave today, only very little percentage that we can really digest very well, but that's okay. It's fun. It looks that our students are enthusiastic actually to learn, although, well, as you said, to learn to understand something takes some time, right? Okay, mari kita berfoto. We wanna have a picture again the way we did it before, like standing up in the front of the podium.